Okay, the people is joining, James.
Nice.
Good afternoon, everyone. We are going to wait a couple of minutes and then we can start the webinar. Okay, James, we can start. Good afternoon,
Nice.
everyone. Today we continue the webinars of the Spain YPN, and today we have with us Dr. James Lofty. Dr. James Lofty is a Humboldt Fellow at Karlsruhe Institute of Technology, investigating micro and macroplastics, transporting rivers using multidisciplinary approaches. He gained his PhD at Cardiff University and currently collaborates with researchers at Imperial College London, the University of Birmingham, and the University of California, Riverside. His work aims to identify the physical properties and mechanisms based on fluid dynamics, which govern how plastic behaves and is transported in turbulence. And today we have the pleasure of James that he's going to present plastic pollution transport in rivers. So,
Very nice. Thank you
James,
very
you
much,
can start whenever you
Bartolome.
want.
Brilliant. Yeah, so hello everyone. Thank you very much for tuning in to listen to me on a very long December afternoon. So yes, I'm Dr. James Lofty. I'm a Humboldt Fellow at Karlsruhe Institute of Technology. And today I'll talk about, as Bartolome said, plastic transport experiments and insights from lab experiments. So the application of experiments that we do in open channel flumes or settling tanks, and how we use these experiments to predict transport of plastic pollution in rivers. So a little bit about me. I mean, Bartolome covered some of these already, but I'm a kind of environmental scientist at heart. I have an undergrad and master's degree in applied environmental sciences from UE and Cardiff University. I did my PhD at Cardiff University, converting to more civil engineering, both masters and PhDs focusing on microplastics, and now as a Humboldt Fellow at Karlsruhe Institute of Technology, focusing more on macroplastics. So why do I study plastics? There's lots of other things to study in the world, but to me, very important. Plastics are one of the most fastest growing materials in production since the end of the Second World War. From 1950 to 2019, we've had over a 250% growth of plastic production and over 459 million tons of plastic pollution just produced in 2019 alone. And in this context, this is cumulatively the global mass plastic production today is greater, or plastic still around today, is greater than the overall mass of all terrestrial and marine animals alive today. So plastics basically outweigh the mass of animals alive today. So where does all this plastic go? 9% is recycled, 19% is incinerated, but 22% is mismanaged, so it's neither recycled or incinerated, or kept in these sealed landfills. 49% are in these sealed landfills. But note that these 49% of plastics in landfills, yes, they may be in secure landfills, but they still are in the environment. They are not completely removed from the environment. So plastics are still exposed to environmental conditions. So they can still leach through soils, they can still be transported in by wind, by runoff. So these kind of leaves with 73% of plastics that are not completely removed from the environment, are also not accounted for. So where does all this plastic go in the environment? So we know that larger plastics break down into microplastics and eventually into smaller, into nanoplastics. They've been found pretty much all over the earth. Concentrations have been found on Mount Everest, the Mariana Trench, in soils, in rivers, in oceans, in animals, in the clouds. But kind of the question for someone who studies or wants to study kind of transport dynamics is, how do the plastics get there in the first place? So how does a plastic item that I've dropped on the street end up in the soils or in the rivers or in the oceans or potentially even into the clouds? So what fundamental processes govern the transport of plastics? Are they mostly environmental processes, the driver of transport? So is it turbulence, is it wind, is it rainfall? Or is it the properties of those particles that drive the transport? Is it because they are very light? Is it because of their density? Is it because of their size? Is it because of their shape? And these are the questions I like to try and answer in my research. Should also remind people that plastic pollutions have many impacts to humans. So looking from a more human perspective, plastics are found in all parts of the human tissue. So from the brain to the blood to the lungs to the arteries to the heart now. And the question is kind of, are plastics inert in the body? Do they not react in the body? Or do they accumulate? Or do they leach, toxic chemicals in the body? We currently don't particularly know too much. But now there are studies that are slowly showing this linkage between plastic accumulations and bodily diseases. So increases in the probability of developing Parkinson's due to accumulations of plastic, or autism in children. And this study at the end here found that higher concentrations of plastics found in arteries led to a higher probability of heart attacks. And this evidence is really starting to grow. As 2013, there were maybe only a few of these kind of studies, and now looking more and more that we're seeing lots more of these kind of studies being published. So these are kind of the impacts of why I study plastic pollution. But my overall kind of research aims, so I mostly look at rivers, plastics in rivers. I want to try and explain how plastics move in rivers. So what are the physical and environmental processes that govern transport? And this basically underpins all transport models and theories. Quantify also the flux of plastics moving around the environment. What is the baseline flux of plastics in rivers? How much plastic is transported per day, per week, per month? Is it all in one go? Is it a constant stream of plastics, or after one flood event, all plastics are mobilized? And this is kind of maybe to support policy development. So if we don't know a baseline flux of plastics in rivers, then we really don't have anything to judge whether plastic pollution is getting worse in rivers, or if policy decisions to kind of reduce plastics in the environment, whether they're successful or not. If we don't have a baseline value, then we don't know whether these policy decisions will ever be successful. And also to predict the fate of plastic pollution in the environment. Where do plastics eventually end up? Are they in the surface of rivers? Are they always in the bed of rivers? Are they in recirculation zones? Do they accumulate only in rivers? Do they accumulate only in the oceans? Are they in the estuaries? This is really helpful for kind of cleanup technologies, but also looking at risk assessment, where the higher probabilities of these impacts of plastic pollution really are. So the first kind of research question we asked ourselves like a few years ago during my PhD was, can we predict the transport of suspended macroplastics in rivers. So one classical model to explain how suspended particles like plastics are distributed in a river is the Rouse profile. And this is a classic steady state advection diffusion equation with advection by settling or rising of the particle and diffusion by turbulence. And this model kind of explains why some particles concentrate near the bed and others are mixed into the water column. And this is a classic equation or theory for sediment transport. If you study sediment transport, and you may have come across this before. And this is determined by the equation here, which expresses how a particle at concentration C at height Z above the bed compares to a concentration at CA at a reference height, which is near the bed. And CA and A are normally kind of the limiters between bed load transport and suspended load transport. And A is normally, we believe we normally use two diameters of sediment particles to have this delimiter. So the concentration of bed load into suspended load. And this expression is governed by beta here, which is the Rouse number, and this controls how the concentration of particle changes with height. And this is calculated through the ratio of the particles settling or rising velocity and the river's shear velocity, so how strong the turbulence is. And on the right is kind of a classical diagram for a Rouse profile for varying Rouse numbers. So we have relative water depth on the left and the relative concentration of particles on the bottom, relative to CA, so this is the limit between bed load and suspended load. And we see that this concentration changes with different values of beta. So a larger beta means that the influence of gravity is greater, the particle travels closer to the bed. So the settling velocity is stronger and the particles are traveling mostly near the bed. And a lower value of beta means that the influence of turbulence is greater on the particle and the particles kind of travel more in suspension. And the profile is therefore more uniformly distributed across the whole water column. So in kind of previous experiments that we've completed over the last couple of years, me and a few colleagues have shown that the Rouse profile can actually predict the suspended concentration of plastics of plastics that are buoyant and non-buoyant within an error of 10% for some particles. So these are some of the relevant publications you can read. This is a few years ago now. And on the left is kind of like a typical concentration profile that you would see for a plastic with a certain settling velocity and a certain shear velocity, with the theoretical kind of Rouse profile in the little crossed lines there. And what we see is we kind of have this suspended transport layer where particles are kept in suspension and where kind of motion is driven by relative settling or rising velocity and turbulence. And this is the area where the Rouse profile is applicable. We also have like a near surface layer in red, and this is where plastics over concentrate. And this is because of surface tension. The plastics hit the surface, and then are potentially, well, some of them are stuck to the surface via surface tension. And in this layer, we don't see any Rouse applicable transport. And this layer is about the same length as the maximum diameter or maximum length of the particle. And this is kind of driven by settling and rising, turbulence, and surface tension. We also have the bed load layer, of course, and this is where particles are always traveling as a bed. And we see that this is driven by, again, settling and rising velocity, mostly settling of the particle, turbulence, and these particle bed interactions, so saltation and rolling. And again, the Rouse profile is not applicable in that area. Now, if we know if the Rouse profile is kind of applicable for plastic transport, then we can really expand on its application. So revisiting this equation for a vertical concentration profile, beta is the governing expression here. And this is this settling velocity over the shear velocity. So if we know a settling and rising velocity of a group of particles, then we can predict its vertical concentration in a river. We know where plastics potentially are in the vertical direction in a river. as long as we have some kind of value for the shear velocity, which isn't too difficult to calculate for a river. So my next kind of research question, this is what I'm doing now for my Humboldt, is to produce a large data set for the settling and rising velocities of the most persistent macroplastics that we find in rivers. And this will feed straight into a Rouse-based model like this. And it's also kind of the fundamental parameters for most hydrodynamic models. So Delta3D would use settling and rising velocities of plastics for their particle tracking models. But first of all, we need to define what plastics we want to test. So we need to, in order to make this database of settling and rising velocities, we need to know what plastics are most persistent in rivers and also near rivers, so on riverbanks. So what we tried to do is decide, when we first looked at what plastics to use, we couldn't find much information on global plastics and what the specific items are that we need to test. So what we did is we undertook a meta-analysis of over 240,000 identified plastics from over 10 rivers and riverbanks. This is across 4 different continents around the world. And we used the OSPAR Litter Index to classify these plastics, which is kind of a common classic method for cataloging litter found in the environment. And it really allows for this intercomparison of plastics across different rivers and riverbanks. This is really easy to put together a meta-analysis if the study had given the amount of plastics that they have in their river in this litter index, because then you could just create a very large meta-analysis. So what we find in rivers that most of them are largely film-based plastics, these flexible 2D particles, while foam particles are most common on riverbanks. So these top 25 items here cover 80% that's found in rivers and riverbanks. So these are the plastics that we need to test for our settling and rising tests. We also need to know what size these plastics are, what shape they are, and also their densities and material characteristics. So using kind of existing databases for lengths and widths of river litter found in rivers, we can kind of extrapolate all that data up and using kind of couplers and multivariate statistics to get the full geometry of these 24,000 plastics that we find in our meta-analysis. So what we show here is the kernel density plots of the longest, intermediate, and shortest dimensions, top 80% of plastic pollution found in rivers and riverbanks. We also have these very similar kernel density plots for density, mass, and volume. And this kind of gives us a complete data set of what plastics look like in rivers and what plastics we need to consider for testing. And what we can show is, plastic bags, large plastic bottles are some of the largest plastics we find in rivers. And again, films and fragments are some of the smallest. We can show that 60% of all river litter kind of have a dimension between 1 and 5 centimeters. So these are relatively small particles. Now, as we know, the 3 principal diameters of the top 25 most common plastics in rivers, we can now predict their shape. So this is based on a very simple ratio of dimensions. The ratio of kind of the intermediate diameter and the longest diameter gives how long or elongated the particle is, while the ratio of the shortest and the intermediate diameter gives us kind of a flatness ratio. So what this graph shows on the left is like a space diagram between flatness ratio on the x-axis and elongation on the y-axis. The values nearer to 1 means that they have dimensions that are all similar in length and are more 3D or spherical. Values near the left are flatter, while values near the bottom are more elongated. So we see near the bottom, we see actually that the plastics, the top 25 plastics actually cluster very nicely into 5 different categories very nicely. So we see that some particles are more 1D in shape, 1D in long, straws, cotton swabs, rope. We see some that are 1D in short, cigarette butts, bottle cans, these kind of shaped or more cylindrical. We have more 2D thin, so these are all flexible film-based plastics, candy wrappers, plastic bags, just random films. We also have 2D thick objects, so plastic bottle caps, metal bottle caps, and also 3D, more 3D items. Foams were mostly 3D, mostly found as a 3D object in the environment. So now we know, so now we have kind of a model for plastic transport. We know what the most plastic, well, what the most persistent plastics are in rivers. We know the geometric, the material properties of those plastics. And now what we need now is kind of the settling, rising velocity distributions for these plastic groups. So now we're getting back to the original very aim of my postdoc. So to produce a data set, settling, rising velocities for the most persistent microplastics in rivers. So to do this, we need very large settling tanks. You see some of these plastics are relatively large. So luckily enough, I've been here at Imperial College London, where they have a very large settling tank, 1.5 meter cubed, not centimeters cubed, meters cubed, settling tank. And this is really to reduce any wall interactions that these plastics may have. We also thought that maybe we should not only examine just the one-dimensional settling and rising velocities, but also the three-dimensional dynamics. We can do much more exciting things with multiple cameras. So we used 3 normal webcams. These are shooting at 1080 HP, at 60 frames per second, nothing too fancy, but they are synchronized together, so they're frame by frame synchronized. And what we can do is we have these synchronized multi-cameras. We have a plastic tracking algorithm that tracks the particle as it rises or settles in these settling tanks. And we can then 3D reconstruct the trajectory of these plastics. And this gives us not only kind of vertical velocities, but also lateral velocities, settling orientation, and also different styles of settling, whether it's linear, oscillatory, drifting, or just chaotic. So next we need to collect kind of a representation of each of the OSBAR categories that we showed before. So we have plastic crisp packets, candy packets, cigarette butts, bottle caps, plastic bottles, plastic bags. We measure the full dimensions, the physical properties, the density, the mass, the volume of all these particles. And then we release them from the surface for sinking plastics and from the bottom for rising plastics. So we use a tracking algorithm that is developed through OpenCV, Python library OpenCV. And this just uses a very classic background subtraction between frames. So we have the original video, we do some post-processing, we then have a background subtraction, and then everything, the pixels that move in that subtraction are then identified as the blob. And that blob is then, the contours of that blob is then detected. And then this is our moving item cross-comparing with the centroid of that particle, and that's what we track. So this is just an example for a plastic bag. And then we use, as we have this, the centroid of the particle from 3 different cameras, and they're synchronized up frame to frame. We can then use a very simple kind of stereo camera setup using ray propagation to estimate the third missing dimension. So we have X and Y in each 3 of the cameras. And then we can predict this missing dimension, the depth into this using a very simple ray propagation algorithm. And this is what we kind of come up with. So this is large plastic bag. And what we can do is then reconstruct its trajectory every frame. Also looking at its settling angle. So this is very important for drag coefficient, and actually looking at what the projected area of the particle is when it's settling and rising. And also the velocities in X, Y, and Z. So we have also, so not only the Z up and down velocities, but also side to side velocities. Or side to side and back and forth. This is a very linear example. So this is a bit more of an exciting example. So this is just a 2D hard piece of plastic. We can see that the dynamics are much more interesting. We see this kind of sinusoidal oscillatory trajectory. which is very nice. And we also can capture these with the different angles and also velocities. Now, so the last kind of 5 months, I've been doing these tests. So on the left, well, I finished these experiments now. So on the left, we have the probability density functions or kernel density plots for the settling in positive and the rising in negative velocities of the top 25 most common plastics in rivers. So what we see is more glass bottles are very fast settling and foam pieces are very fast rising. Rise very quickly while glass bottles settle very fast. We see that most particles line up between -15 and 15 meters per second. Most of these are kind of the plastics and the most common items, whereas we see heavier beverage cans, metal cans, are more settling much faster. So we have over 1,000 individual trajectories. So these tests are tested over 1,000 different particles, and we have at least 30 repetitions of each OSPAR category. So this is kind of the end goal of one of my postdoc aims. And we find that 80% of river litter have an average settling or rising velocity between -20 and 15 centimeters per second. So if you're going to use kind of a hydrological model in Del3D or something, if you wanted to capture the settling and rising velocities, or the majority of settling and rising velocities of macroplastics, then these are the values that maybe you should use. So coming to the conclusions now, we now have for the last few years, we now have a model for the vertical position of suspended transport of plastics. We know what the most persistent plastics are in rivers. We know their geometric and material properties of the most persistent plastics. And now we have a settling and rising distribution for these litter groups. So what I'm doing now is now looking into kind of a full characterization of settling rising dynamics. So this includes not just velocities, but also looking at oscillation, amplitude, wavelength, whether these particles drift, whether they are linear. And this is really important to looking at dispersal and how we can explain some of these distributions. So if a particle drifts more, then maybe in a river, maybe it drifts more laterally or has a higher dispersion in the river. And I want to integrate all of these different data sets, these large scale data sets, into a fully open source database for anyone to use for a hydrological model. So hopefully these kind of data sets will be fitted into anything you want to use for modeling plastic transport. And yeah, that's it. Thank you very much for listening. I'm very welcome to any questions or suggestions from anyone else.
Thank you very much, James. So
No
in the
worries.
chat, we can have questions. So I'm going to break the ice. I'm going to ask you 2 questions. I'm into modeling and I really like your work there at Imperial. I've considered many times, but I have a question like, when you, in your 1,000 experiments, we've been talking a lot that there are some different rabbits that have different motion, and if I want to model, what is the rabbits that you recommend me to have special attention because of the movement, the trajectory? What is the one type or different type that we should learn more about it and we should take care of the result of the model because it's quite difficult?
Yeah. So that's a good question. I kind of break it down maybe into two different things, but definitely in terms of dynamics, if a particle had much more lateral drifting motions, then maybe that should be specialized maybe more as a laterally drifting particle. So you have particle with larger dispersion compared to most of these models are based on just a spherical particle. But if you had a particle that drifts significantly more than it does vertically, then maybe that should be having special attention to in terms of modeling, because it may even hit a riverbank before it hits the bottom. but also looking at particles that change their shape in turbulence. Obviously, all these tests are conducted in still water, but when these particles are going to be in turbulence, they may change their shape completely. Plastic bag may change its shape, therefore its drag, and therefore its circulating velocity as soon as it goes into turbulence. Um, so maybe more work needs to be done on how circulating velocities change in very, very small turbulence, or how the shape changes in very, very small turbulence, which would refine some of the models that you would use.
Thank you, James. My second question is about more or less about the same, but I don't know if you are going to work more on plastic movement. For example, in your setting tank, are you going to
Mm.
have different type of plastics, the interaction between them, like a plastic bag and different cans, or
Yeah, that's maybe the next experiment that we do is so these are all singular particles settling under their own buoyancy or rising under their um, buoyancy. But the next kind of idea was to use multiple plastics at the same time to see how that affects their circulating velocity. So one plastic bag versus two plastic bags versus 10 plastic bags versus 100 plastic bags, that really affects their circulating velocity, and then you have this hindered settling effect. Um, so yeah, that's kind of the next plan um, for experiments.
and if I remember well, I think all the codes and all the information is available, isn't it? If I remember, so
That's
if
it.
anyone
Yeah,
want to use it, the only thing is they have to download
yeah,
download the code,
yeah,
and if they have any question, they can
yeah.
ask you.
Yeah, so all these data sets will be available online, probably in a GitHub repository. Same with the camera detection codes and 3D reconstructions, completely open source. So I, I hope people will use them. Um, but yeah, that's kind of the idea, is to generate these open source data sets that anyone can kind of download and just cite wherever the paper would be. Um, for their own models. I mean, that's the aim for these experiments.
So if anyone can ask in the chat, now is the moment. Well, we don't have more questions, but if anyone can ask James after the webinar, or if someone is watching it on YouTube, they can send James an email that is on the presentation, and I think it's also on the web page. So,
Yeah, yeah, emails on the first slide of the presentation. So if you have any more questions, then go ahead and ask.
so many thanks, James. A really nice presentation and really, really interesting. So we are waiting to see that paper published, to use it.
Yeah, yeah. I'm also waiting for it to be published as well.
So thank you very much again.
No worries, and thank you for having me.
Have a nice week and a nice Christmas.
Yeah, and you, Barton, and you.
So thank you very much, James.
Speak soon. See you later.
See you.
Bye.
Bye.